Okay, welcome back. So coding session. We're gonna code the Cauchy endgame, or at least we're gonna try. So let me pull up a terminal and share my screen. Share. Just to go. Great. So there's my screen. There's my Julia. None of you can see anything, so let's zoom up. There we go. By the way, I mentioned it's easy to run Julia with multiple threads at its disposal, and this is how you do it. Okay, do not put a number there bigger than the number of threads on your computer. If you want to know how many threads you have on your computer, Google, how do I know how many threads I have on my computer? Okay. Okay, I have loaded homotopy continuation. I have loaded plots, and I'm going to start pushing in these functions that we did last time. Okay, just one at a time, just so we can all remember what's going on. So this was Newton's method. It took in a polynomial and a guess of a root and the variable, and it gave the Newton, it applied Newton's method to that guess and gave the output. This was a thing to make an animation. I have edited it a little bit for this lecture, in that now the solutions, which are like kind of fixed in this whole animation, those are optional inputs. There's the Bezier start system. There's the Bezier start solutions. There is the Bezier homotopy, also known as the total degree homotopy, with optional gamma, but the default is just 1 plus the imaginary unit over the square root of 2. There's the chain rule, and there's an Euler step to solve a differential equation with some initial value. There's the predict correct process, which takes in a single solution, a differential equation, step size, a homotopy, some variables, and some number of Newton iterations. Great. Okay, and then some of this is automated by like automatically writing the differential equation and tracking things and all that, and that's called track solution. You just need a start solution. It knows that the t-value is t equals 1 kind of thing. Great. All right. And then I wrapped that all together, because I guess we didn't do this last time. I was surprised, but into something called myself. So now we can do, for example, f is x minus 1 times x minus 4. Mysolve fx, please. And it should do something. There we go. Boom. Yay. Yeah. So what has it done? Let's take a look. Very nice, we had some output going on. So it looks like we output the homotopy. It says, okay, I'm tracking this start solution. Here's the homotopy. Here's the Davydenko differential equation. I Euler predict. I Newton correct twice. I Euler predict. I Newton correct twice. Over and over and over again, until we get that the Newton correction at the end gives us -1 as a solution at t equals 0. Okay. And then it does it for the next one. And then it does it for the next one. And it's great. Okay, very good. Any questions? Okay, where is my mouse? There, okay. Sorry, I've lost my mouse. There we go, okay. All right. Okay, so now I want to code an endgame tracker. Okay, so what's this gonna do? This is going to like stop at like some small epsilon and then do loops until it comes back to where it started, and then take the average of some sample points it takes along the way. That's the idea. But we don't know how to do loops yet. We don't know how to do little loops. because all we know is how to cook up the Bézier homotopy and travel from t equals 1 to t equals 0, right? This was when I realized, oh, wait, I haven't talked about going from one t value just randomly in this picture to another t value randomly in this picture, but you can do that, right? That's what allows you to do the Cauchy loops. So let's get a function that does that. Okay, so here we go. We're going to call it straight line track. Okay, it's going to take some start solution and it's going to want the solution some target system. F will still be our target system. G will still be our start system. X will still be our variable. We still put in a step size. And now I want to include something that says stop app, which in general, the default is 0. At t equals 0 is what we're after. Okay. Print line, tracking, start solution, start solve. Okay. So we have to include some t variable, put our starting solution in this this homotopy space, right? So we need the t value. Cook up the straight line homotopy. Write the Davydenko differential equation. No. No gamma. So it might be dangerous, is what you should think. But as long as we're essentially choosing generic points as t values, we won't have an issue. Okay. Great. So now we have this path where we have a start solution, and while the current solution, the t value, so that's a second element, is greater than where we want to stop at, the step we want to take will be, well, it's going to be a negative step. Well, we're either going to take the full step size of a step, or we're just going to drop ourselves down to stop at. And we predict correct, current solution, differential equation, step size, h, and xt. That was our syntax, and now we're stuck with it. So there we go, and now we print, we push it into the path, and then we keep on doing that until we get to where we want to go. And why not just say the final t value we computed was this t value. Okay, and then return. Let's not return the whole path, let's just return the last thing in the path. Okay. Good. So now, theoretically, I could have f, which is like, well, what is our f? Okay, great. So we know the solutions to that, right? I mean, they're right there because it's in the factored form. So let's make a g, which is a random polynomial. So random complex of 64. Let's see, I and 0 to 3. Okay, so now I should be able to straight line track, for example, the start solution 1. I've got my G's and F's backwards. So now F is going to actually be my starting system and G will be my target. So I got to swap those places. Sorry about that. And step size equals, say, negative 0.01 just to be safe. Awesome. Great. So I think the issue, so this is good. So this is a good thing. We are seeing an error happen with somebody who does this all the time, and we will figure out what's going wrong. This is very good. Not a lot of people get to see this process. Everybody has their own little way. 1 is very suggestive that it's an integer. I may not want to add a complex number to an integer or something. So just to be safe, that is also 1. But now it is pretty unambiguous that this is a complex number. And we're, okay. So how did I know how to do that? Well, the real answer is that's happened to me a million times before. Okay. And what I'm seeing just by glancing here is it says something about real. I'm like, oh, okay, I know what it is. Like, why is this system, this computation I'm trying to do, have anything special to do with the real numbers? Oh yeah, because I'm tracking 1 as a start solution. Okay. Great. And what else am I seeing? So I'm seeing in number 3 here in the output, it says push. We're trying to push something, which is a complex F64. That's the second argument of push, into something which is a vector of integers. Well, that's a problem, because then I'm going to have to change the type of the vector I'm pushing something into. Right. And it doesn't want to do that. So that's the error. And that's how you can tell. You just look at it like that. Okay. So anyway, so we got something. No idea if it's correct yet. So let's call that A. And can we just do G of A? That'd be cool. No, evaluate. Gx goes to A. Okay. Depox test passes. Was it you who suggested just to plug it in and check if it's really small in like our second lecture? No? Okay. Well, it's all recorded, so I'll check. Yeah, so this passes our test for the most part. If we wanted to, yeah, okay, so now maybe I wanted to animate this, but it's a problem because I wanted like a straight line thing and I didn't output the whole path, I just outputted the endpoint, right? So what do? I go back to the function and I add some optional thing and then if return path is true, return path. Otherwise, do what you were doing anyway, right? Now, this is not going to cause any issues unless somebody actually puts in a different option than return path equals false. So I do want to animate what happened. So I want this the path with return path feature. And so theoretically this works. And I just have to find the temporary file location on my computer, whatever that's it. There it is. Wow. Sorry, something's certainly moving here. What's G? What's F? Okay. F is that. G is that. Because all of a sudden my output here is not actually the output I got before, right? So the last thing here is 1 point something plus 0.6 something, right? But A, oh, it was that. Okay, that's funny. Well, let me show you the animation I'm seeing. You'll see the concern. Yeah. Awful aspect ratio. Oh my gosh. Ah, okay. If you look long enough, you can see it move. Just look long enough. So, oh, it's moving, right? So see it moving? See it? It's moving. It is moving. Okay, nothing's wrong. Nothing's wrong. Good. All right. Great. Let's move on. Okay, so now we can, now we can track things around. All right, what did we actually want to do though? We wanted to handle this endgame. So let's make an endgame function. We'll have some solution, we'll have some homotopy, we'll have the x variable, t variable, and the number of sample points we want to do in our Cauchy endgame, okay? Line, starting end game at t at, let's just say so, whatever that solution is, okay? So solution is going to be an xt value. So xi and e. So instead of calling it T. I'm going to call it E for epsilon. Okay. So now here are my data points. So instead of going around an actual smooth circle, we're going to do a polygon with n vertices and just do straight line homotopies. Okay, so those are our parameter values we want to visit. Okay, they all have epsilon modulus at different angles, equally spaced out. Go all the way around. Okay. All right, so cycle, well, let's say, okay, let's make a path. The game path is gonna, okay, well, it starts with xi, great. The cycle number will start as 0. And we now want to do a loop. We want to keep on going around these parameter values until we get back to where we started. Okay. And just in case we screw something up, because it's going to be a while loop, right, we're going to keep on doing something until some condition is met. Very dangerous thing, because when you code, if that condition is never met, your computer will be in an infinite loop. And we want to avoid this. So just in case, we're going to say while the cycle number is less than 100. Okay. We are not dealing with anything with a cycle number bigger than 100. So if it goes around 100 times and isn't stopping, it should just stop. Okay. And okay, I want to go around at least, I mean, I want to do at least one travel, right? So what?
I'll just watch.
Are we good? Did I miss something up?
I don't know. You're gonna be short one closing bracket unless it comes later.
Oh, it's gonna come later. I promise. Yes. This is or. So double ampersand or is and. Double bar is or. And what do we want? We want the last element of our path to be really close to the first element of our path. So when that's not happening, when it's significantly different, we want to do something. And what's that thing we want to do? We want to go around once. So cycle number gets incremented. Okay. And now we need to track along those values in single circle. Okay, so that requires n steps. So we're going from single circle I to single circle I plus 1. That's the t values we're tracking. The thing we're tracking is the last thing in our endgame path. Our target system, well, let's do our start system first. Start system. Well, we just have to evaluate h at the start single circle up. And then our target system will be evaluating h at single circle I plus 1. Cool. And now we have this really nice function, straight line track. And we want to track this solution, the target system, from the start system. And I think we have to include an x there. Okay. Great. Do we want to screw with the step size? Let's not screw with the step size yet. Okay. Push. Okay, after we do that, we just stick that at the end of our endgame path. Close up this loop. Close up this loop, I think. Yeah. We want the average of everything. think that is good. The big one. Okay. So now we pray. Let's do something. Great. So let's do let's get an f with a singular value. How about x squared? Yeah. We like that one. We know that one. All right. Let's do the myself, but stop at 0.1. And we're going to use no gamma trick. In other words, our gamma is 1. Cool. That's great. Okay, mysolve doesn't output any path really. So okay, that's fine. Okay, so there we go. And let's do an end game on the first one here. Well, let's first just do a sanity check. What is the square root of 0.1? So this was the example we had before. We're just computing the square root of t. Okay, and we've chosen to stop it at t equals 0.1. And these were the solutions we got, and good. Okay, so that's great. We're correct up to many decimal points. Okay, now we want the end game path and the cycle number and the guess to be the output of the end game that we just did. So we have, did we call this thing S? Yes, S. So this is S1. So this is, yeah, the first path there, this negative 0.316 comma 0.1. Okay, and we want the Bezier homotopy from fxt with gamma is 1. That's the homotopy. We're doing this all over. X and t, and let's do n equals 20 so we can get a nice animation. Awesome. Okay. Will this just work? Oh, great. Cool. Very nice. It is going around. Yay. Okay. Maybe we can here, let me do this. E.g. this equals, let's do it with the other solution too. So instead of the end game applied to this first solution, we'll do it to the second. It also, and it knows the cycle number, right? And it has this guess. And so we can just add that to our list. And because I think we were super clever with the animation, this should just work, but maybe not. Maybe we have to reshape things or something. Yes, I think we do have to reshape things. Because we get this picture. Okay. Whoops. Okay, so syntax for the make animation didn't work, but we see it's going around in a circle, yeah. Okay. So let's reshape this. And 1 second. Let me see how big it is first. So it's 2 elements, each of which is 41 elements long. And now it's a 2 by 41 matrix. So we either want it to be 2 by 41 or 41 by 2. We'll see by just checking. Okay, there we go. Okay. That is what we wanted. Yay. Beautiful. Okay. So as we go around, I mean, keep your eye on one. Goes all the way around back to where it started. I put in a bunch of frames of a pause at the end of the video, so you knew where it starts and where it ends, by the way. And the average of all those values you're seeing is the origin, because that is the solution. Okay, let's soup it up. Okay, let's do it. Okay, we're going to try to solve f, but we're going to stop at 0.1. Actually, because this is a more complicated thing than just this quadratic one, we want to be even more careful. We want to make sure whatever loop we're doing at the end doesn't enclose more than one point of the exceptional set. Okay. Otherwise, it won't work. Actually, you know what? Let's do it the bad way to see what happens when we do it the bad way. Actually, okay. So now I think this is all fine. We're gonna track yeah, really good. I think that's good. It's actually not too bad. I mean, I don't know what the fuzziness is going on in there, but seems okay. Maybe it's worth actually at this point changing the window size to something more reasonable. So let's make them options, of course. There we go. So yeah, so e.g. the last thing was there, so we could now theoretically make this a much better window. Because we're going to be doing itty bitty loops, which means these things will move itty bitty. And so we definitely want, bye. Comes back. Okay, maybe that wasn't the best window. Should have made it a little bit bigger. Okay, so leaves, comes back. Okay. Great. Any questions so far? Does it make sense? Okay, let's just try to do it to all of them. Okay, so we're going to try to solve all of these via the Cauchy endgame. So remember, f looks like that. It has a root of multiplicity 3 at x equals 1. It has a root of multiplicity 3 at x equals 5. Okay. Okay. So endgame list. We want to see all these paths. S. Yeah, it's my solve. Good, got it. 6 solutions, great. So for S and S. Cycle number and the yes, the end. T and n equals. Okay. Cool. So yeah, let's see what's going on here. Does it actually tell us? Oh, computed the cycle number to be 1. Ah, that's bad. Well, okay. All grist for the mill. Let's see it. So I think the reason why it thinks something has cycle type 1 is because we did not get sufficiently close to t equals 0. So in other words, we were not in this nice endgame region where we are close enough to t equals 0 that a circle of that modulus doesn't have any exceptional points in it other than t equals 0. Right, so we're encapsulating more than one exceptional point in this loop. So what we're going to do is we're going to reduce this this place we're stopping at to be something smaller. So we're going to stop at 0.001. Okay. Awesome. We might see us get to 100 cycles if I don't stop it. So this is an infinite loop for sure. So I'm gonna hit Control C. Uh-oh. Well, it'll stop when it gets to 100. So this is what I get. So and I know what happened. This is what I get. This is the first statement. I know what happened is the second statement. It didn't use a gamma trick. And that was absolutely fine. There was no problem with that, with the x squared equals t, because the only exceptional point was t equals 0. Okay, but for us here, that's not the case because we're following a degree 6 star system, right? So there might be exceptional points, which means we have to use the gamma trick. Otherwise, we won't get the right solutions. Gamma equals gam. That still doesn't look great, right? Okay. Let's do a different thing. I don't want to in real time figure out what's going on. So here's this. Here's this. So this is one that I've pre-computed, at least. So sorry, it should be myself. Great. I was too ambitious. I flew too close to the sun. Here we go. Yay, cycle number 3. Okay, so S1 has cycle number 3. The Cauchy guess is the last number there. It's about -2. And indeed, F has -2 as a root of multiplicity 3. I don't know exactly where things went wrong, but let's do this for everybody now. Good. So here are endgame paths. So they're length 61, 61, 61, and 41, and 41. Why? Because I wanted to take 20 samples, right? So anything of multiplicity 3 should have 60 points, except we need the 60 first to know that we've arrived back where we started. Okay, so I could make animation hcat g list ... but maybe I only want the first 3. This gives me a matrix. You have to have the same one. There we go. Okay. Make animation. It's worth noting, these are involved algorithms. Oh boy, look at that. Yay. Okay. Cycle number 3. Okay. The other thing I really want you to observe here is that, so we've stopped at some very small t value. Right, so they're supposed to be really, really close to the solution. The average would be a really good approximation, wouldn't it? Right, so the average as these things rotate is the Cauchy integral. But even if you just picked a fixed frame and you took the average, that would be a good approximation. It's not crazy to think that the trace would be a nice endgame. Okay, and these are colliding in the configuration of like third roots of unity, like a regular triangle here. That's also not an accident. Okay. Okay, anyway, so it works. You can't even check the guesses. Not bad. Looks like 3 -2s and 2 3s. Okay. And we can compare this to trying to go all the way to t equals 0. Which is actually also not bad, but it's not great. We have many more digits of accuracy when we do the Cauchy endgame. Okay. And we should actually see that the higher the multiplicity, the less accurate we are. Okay, so the multiplicity 3, 1 is -2. And there I see us being off by around a couple hundredths. Whereas for the one of multiplicity 2, the number x equals 3, we're off by a couple thousandths. However, in the Cauchy situation, maybe we're off by a millionth, I think. Okay. So it really is a better way to find these roots. Any questions? Okay. I would actually like to try something a little bit more ambitious once more. Let's try something with a multiplicity 6 root. Okay. All right. So we tried this with multiplicity 6. And see if we can get roots this way. Yay! Cycle number 6. I like it. great. It really can do higher order stuff. Ah. No, this is bad. Yeah. We did not stop close enough. Nothing was in the x=3 path. So we didn't stop close enough. And not only did we not stop close enough, well, I guess the reason we're getting multiple roots is because we didn't. No, actually, I'm not sure why we're getting multiple roots. We must have had a path crossing. Are we getting multiple roots? Yes. Change the gamma. Change the gamma, try it again. Because we are getting some correct answers here. So, be a little bit more pessimistic with our path tracking. Keeping in mind that our path tracking really is the most naive path tracking version one could implement. And then we'll truck around these loops once more. Let's see what we get. Okay. Yeah, it looks like I'll get some that are 3 at least. That's great. Okay, so that's S. And yeah, now we wait. Yeah, and I'll post all this code. And this all happens automatically in homotopy continuation.jl, by the way. So homotopy continuation is doing it's doing very smart predictors. And it is monitoring condition numbers, which we haven't talked about yet. We'll talk about that with the multivariate homotopy continuation section, which is the next section. But it's monitoring some measurement of how close it is to one of these bad points. And it uses that number to adjust how pessimistic it is in its path track. It's called adaptive path track. And yeah, and then it'll do the Cauchy loop, and I think it actually even nice. Okay, computes a power series endgame. Okay, so obviously this has not been fantastic. Let's see. Length. Yeah, so none of these actually came back. So there's some tolerance that's wrong or something like this. So yeah, these numerical adjustments matter, especially when you're trying to extract discrete information like you're required to do in the Cauchy endgame. So in the Cauchy endgame, it's not enough to just give somebody a floating point number back. You have to give somebody a natural number, which is the cycle number. You have to know when to stop. You don't get to be off a little bit about how many loops you take. You have to be right. You know, so information like that, extracting that information from numerical measurements is tricky because you have to decide whether or not 2 floating point numbers is the same, right? I come around, oh, it's a little bit different. Does it count as different? Does it count as the same? And a lot of issues with numerics boil down to determining whether or not 2 floating point numbers are the same, or equivalently, whether or not a floating point number is 0. Okay, so this is not easy. And that's the issue we're seeing here. So even though at the end of this, yeah, we are getting 3, which is one of our roots, it's not recognizing that it came back to where it started, because my tolerance for deciding that is too optimistic. Okay, so we're seeing a lot of the features of numerical calculations appearing here. Okay, but the concepts are good, and we saw some animations. Code's right, just gotta fiddle with the tolerances. So feel free to play with that at home. That'll end the lecture for today. Thanks for coming. And I will stop it and then ask questions.